If we take a gaseous system at equilibrium, we can derive a value for the equilibrium constant either using partial pressures or using concentrations. Let's have a look at this system here. We have got dinitrogen tetroxide in equilibrium with nitrogen dioxide. And the fact that we can derive even an equilibrium constant either by pressure or by concentration tells me that these two constants must be related. In this video, I'm going to show you how. The link is in the way that we can work out the number of moles of gas in our system at equilibrium. Now, we can calculate the number of moles of a gas in two ways. Firstly, number of moles of a substance is equal to the concentration times the volume. So, number of moles of NO2 would equal the concentration of NO2 times the volume. And the number of moles of N2O4 would equal the concentration of N2O4 times the volume. However, we can also work out the number of moles of a gas using the ideal gas equation. PV equals nRT, where T is the temperature in Kelvin and R is the gas constant. So using this expression, the pressure of NO2 in our system at equilibrium times the volume is equal to the number of moles of NO2 multiplied by RT. And the pressure of N2O4 in our system times the volume is equal to the number of moles of N2O4 multiplied by RT. So, step 2. Combination, we'll call this. So thinking first about the NO2, PNO2 times the volume is equal, well, we've seen that we can take the number of moles because the number of moles equals the concentration times the volume. So this is where we are going to put in the concentration of NO2 times the volume times RT, and the pressure of N2O4 multiplied by the volume is going to equal the concentration of N2O4 times the volume times RT. And we can see straight away that volume on either side of the equation is going to cancel out. Step 3. Let us recall the expressions for Kp and Kc for this system. So Kp would equal the partial pressure of NO2 raised to the power of 2 over the partial pressure of N2O4. And Kc would equal the concentration of NO2 raised to the power of 2 over the concentration of N2O4. Now we know that the partial pressure of NO2 is actually the concentration of NO2 multiplied by RT. Now it's been raised to the power of 2, so I'm going to raise that to the power of 2, and I'm going to raise RT to the power of 2. And the partial pressure of N2O4 we also know to be the same as the concentration of N2O4 multiplied by RT. I have RT both above and below the line, so that's going to cancel out, and one of those is going to cancel out. So we now have an expression that tells us that Kp is equal to NO2, gas, concentration of, to the power of 2, RT over concentration of N2O4. And we can see that this little part of our expression is exactly the same as the expression for Kc. So pulling this together, we can say that for a gaseous system of equilibrium, Kp is equal to Kc times the gas constant times the temperature in Kelvin. Isn't that neat? If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.